We are discussing the advanced topic in fluorescence. These topics are typically used in our research problem, and like everything that I discussed was used, but these are little advanced. So, if you remember, I had talked to you about this concept of fluorescence lifetime. Remember how much time it takes to come from the excited state to ground state. That is a fluorescence lifetime. So, time elapsed between the activation of a fluorophore and emission of a photon from fluorophore, that is called fluorescence lifetime, right. Fluorescence lifetime is sensitive to the local environment. If it is here, it has a chance to decay faster. If it is, it has time to decay slower. So, that is one of the concepts that we are going to discuss today. Another one we are going to discuss is fluorescence resonance energy transfer, right. Simple concept. This is my fluorophore and here is sitting my fluorophore. I want to measure the distance of these, static difference as well as a difference that is happening because of dynamics. Because I keep insisting protein has a very dynamic personality. It breathes, it moves. Those distance can be measured by this technique called fluorescence resonance energy transfer. You can use as monitor for intracellular biochemical reaction, and another concept that we will be discussing is called fluorescence lifetime imaging film. So, if you see fluorescence after a pulse, so here what you have to do, the concept remains very simple. Lifetime is nothing but rates of radiative and non-radiative, right. So, tau, which is fluorescence lifetime, is 1 by Kf and Knr. F is rate of fluorescence, Knr is rate of non-radiative emission. So, it goes to excited state, it can come back by giving you light, it can come back by not giving you light. That is the time is called fluorescence lifetime. So, sum of rate of constant of radiative process Kf and non-radiative process Knr, and measured fluorescence lifetime tau is numerically equivalent to average lifetime value that we have. So, you can take it as average and molecule remains in the excited state. So, if you look at different fluorophore, they have a different lifetime, like retinol, reactive orange, malachite green, auramine, all of these. So, lifetime is in picosecond, right. 11, 32, 1.18, less than 100, less than 130 and 61. These are the lifetime that we have of a different fluorophore. I mentioned that it is a rate of decay. It can decay faster or it can decay slower, right. So, here one can decay, if you look at here, it is a fluorescence with a lifetime of 0.2 nanosecond fast, and here lifetime is of 1 nanosecond. That is a slow decay, fast decay. While we are exciting, if you look at excitation I am doing here, I am exciting with a laser pulse, ठीक है, line तुम देखो एकदम sharp line है. I am exciting with a laser pulse and I am detecting how it decays. If it is decaying fast, sharp decay. If it is decaying slow decay lifetime is longer, right. So, that is the one way. So, this is a property of a fluorophore that is giving some idea about the environment. Now, my fluorophore, suppose this is my fluorophore, here is my tryptophan. When it decays fast, like this or like this, slow or fast? If it is buried,
slow.
Decay slow. क्यों? What is decay? De-excitation. If it is buried inside, excitation twice happen. If it is buried inside, it will decay slow or fast. Why? Decay is a rate where it is giving energy to other molecule. So, here probability of decaying, giving energy is higher or lower?
lower. It can't give to other molecules. Like,
Why? All molecules are sitting around, right? And here nothing is sitting around, only solvent is there. So yes, you are right, it depends upon what is in the environment, but probability can be different if it is buried inside, and but also depends upon what kind of other molecules are surrounding, right. So that gives you idea about the surrounding of the fluorophore, buried, exposed, what is near, which kind of molecules are surrounding this, that is there. So let us look at one of this example. ANS, I have explained to you, ANS it is a fluorescent dye in pure methanol and water methanol mixture, fluorescence lifetime decay. ANS is a dye, you remember where it binds? ANS is a dye, it binds to protein, but a particular surface of a protein. NS is a fluorescent dye, it has a specific binding to the exposed hydrophobic surface area of a protein. Therefore, it is used to find it out if protein is in molten globule state or not. That is a simple concept that I want to impart upon. This I have already explained to you, right. Protein is in folded state, not too much hydrophobic surface area is exposed. If it is in unfolded state, everything is exposed, but in something called a intermediate state, जो हाइड्रोफोबिक अंदर रहना चाहिए वो भी बाहर दिख रहा है, दैट्स स्टेट, दैट्स कॉल्ड मोल्टन ग्लोब्यूल स्टेट. इफ यू हैव स्टडीड प्रोटीन फोल्डिंग इन बायोफिजिक्स, you might be knowing this concept. If you don't know, it's okay. This is the dye that is used for detecting that state. Now this dye, if it is sitting in methanol, it's giving you red. If it is sitting in water and methanol mixture, it is giving in blue, right. Excitation is happening by this laser pulse where it is black. So here a mixture is making it fast decay and methanol slow decay. So it is the dye decay is also depends upon the solvent. Pure solvent, methanol decaying slow. If you mix it solvent, it's decaying fast. So kind of like a solvent, it changes the fluorophore. Now how do you measure this, right? So lifetime, as I said, excitation is not being done by a typical like a whatever tungsten lamp or whatever, you are doing with a laser with sharp one. So you require a different kind of setup. So lifetime can be measured in either frequency domain or time domain data, because we are measuring with a time, right, how the photon is coming, and it involves the illumination of time with a short pulse of laser followed by the measuring the intensity against time. That is what we are doing it. So typically you require a little fancier instrument for doing this experiment. You require a laser source that should come through fiber optics, shining to the sample is going to excited state, giving it, and then you count the each photon that is coming. So that one can do with a emission filter, single photon detector, and you plot it, the decay in the intensity as time passes. So here is the plot, probably if you can see it, IT is the intensity at time t equal to I0, which is the initial intensity, e to the power t divided by tau 0. Tau 0 is the lifetime of the fluorophore. So that is what you measure using the single photon counting experiment, and this is the total setup that you have. This is called time correlated single photon counting experiment. Okay? Time correlated single photon counting. Where you can get this instrument? Anindra Datta ke lab mein jao, you can get this instrument, which is there in chemistry department. So this is called time correlated single photon counting. It is a common technique that measures the fluorophore decay with the time domain. That is what is our excitation, and we are counting the photon as it decays, right. So here is the excitation pulse, optical waveform, and you count the photon as time goes, and finally if you remember this kind of curve I was getting here, it is a simple one, but this is doing each photon counting. So single photon events are detected and their time arrival is correlated with the laser pulse that was used for excitation of sample. A little complicated, but it can sit on a table and you can use this concept for understanding the dynamics of that. So idea is simple. You have to have a laser pulse, a sample, the photo detector, the timing electronics, and one can have each photon counted like that. So, here is excitation pulse and this is fluorescence coming, and you are counting photon when they come on the time. So, that is the time, the signal coming in time domain, and finally you take everything, it looks like this. So, I give you the same protein example that we had done, right. Remember this protein, 2 domain, 2 tryptophan, silenced one at a time, right. I use this example for telling the involvement of this single tryptophan by quenching experiment that is done. I found that where the protein is in the quenching state or not quenching state, but here I am using this single photon counting experiment for understanding the dynamics, right, doing like this or buried like this. These 2 tryptophan, one is relatively free, another is little buried, and one can do this experiment and you can find it out the lifetime that is coming in nanosecond. So, look at this one. So, here is one and here is another, right, 2 tryptophan. Here is, you forget at the moment this one, which is also significant, but this is this counting that we are going. Although we could not find much significance in the lifetime of this, it was modeled experiment said that this was very flexible, this was buried, but our experiment did not give it. If you look at this data is non-significant, you have to do 3 times, that is why you get error bar. All looks slightly different, but if you put the error, it is not that significant. So, it says that both of them are relatively same decaying function. There is another called beta component that is tell about tumbling. So, here there was a difference, but here like in the lifetime that not much difference. So, that is kind of experiment you can say. Now, I am looking at the tryptophan, doing the single photon counting to understand how they move. I can also look how protein tumbles in the solution, just looking at that, that is the correlation time you can find it out. So, that is use of single photon counting experiment, right. This already I had discussed little bit with you, anisotropy measurement. It is called anisotropy. What is anisotropy? Isotropic and anisotropic, these two things. What is isotropic solution mane or anisotropy? What is anisotropy? Orientation dependence is anisotropy, orientation independence is isotropic, right. So, suppose my molecule is somewhere sitting here and it is solvated by the signal. One can have a time dependent stock shift, its molecule start tumbles, right, then it is in an isotropic environment. You can do this, like if it tumbles here, the molecule was sitting like this, then it can go like this, you see an intensity decay. This gives you something in experiment called polarization anisotropy. So, what you have to do, it is just probing how my molecule is orienting in the solution. If it is orienting without any intensity change, that means it is isotropically moving, but it changes the intensity, that means in this is preferred, this is going less, less, less. So, there is an isotropic dependence, and that is what you measure in something called polarization anisotropy measurement. So, what you have to do, you take the intensity at 2 angles, one is parallel with time dependence, another is perpendicular at the time dependence, and then divide by the total intensity. This gives you polarization of the fluorophore. So, polarization intensity you can do it. So, you can have a use diluted sample fluorophore for this kind of experiment, and then you are putting your detector vertically and horizontally 90 degree per. If you look at that is I parallel, I perpendicular. So, you put it. So, tryptophan locked in a place where if the tryptophan in the solution is not bound and it is excited, it can have different kind of orientation. If it is buried, it can have a different kind of orientation. That gives you idea about anisotropy. So, information about the size, shape of a protein, rigidity, various molecular environment you can find using this experiment called fluorescence polarization, right. So, fluorophore preferentially absorbs the photon and whose electric vector is aligned to the parallel of transition dipole. In an isotropic solution, fluorophore is randomly oriented. In an anisotropy, it is not randomly, it is either at this angle or this angle or this angle. That is what we are measuring here by putting the detector at two angles. So, absorption transition dipole is parallel to the electric vector of excitation, and you can measure this anisotropy or something called polarization. It is the same measurement, just the 2 is changing here. So, you can have a parallel intensity, perpendicular intensity, and then plot it, the polarized light, and find the polarization or the anisotropy using the same experiment. So, that is a rotational dynamics, you can find it out. So, if you look at the same setup, what was that? Single photon counting experiment, excite with a laser, and then you measure parallelly and perpendicularly, and you can plot it how much change it happening, gives you fluorescence anisotropy measurement, which tells you about the molecule that is there. So, where are the application of this concept of fluorescence polarization or anisotropy? Extremely important in say antigen antibody binding. Suppose I have tagged a fluorophore on antibody, and I want to see if my antibody is binding to antigen or not. This is the way you can do it, measuring the fluorescence anisotropy. So, in your opinion, what is going to change? I have an antibody, I have a fluorophore on the antibody. Antibody is like this, here are my two arms, it is binding to say antigen, or it is not binding to antigen. What is going to change? It binds to antigen, क्या हो जाएगा? हाँ, दोनों में से कुछ चेंज होगा, और हम मेजर कर रहे हैं कि बाइंड होकर ओरिएंटेशन चेंज हो, ओरिएंटेशन डिपेंडेंस हो रहा है या नहीं. So, if it is not binding, it is tumbling freely. If it is binding, motion restricted. Motion restricted can be shown in anisotropy. So, if it binds, your motional restriction introduced, you can measure that using anisotropy. So, this is an extremely interesting simple tool for screening the binders versus non-binders. Antibody जब हम डिजाइन करते हैं, so we come up with many antibody design and we screen it which is binding effectively. This is the way you can find a binder versus non-binder in antibody antigen reaction. Understand the dynamics of protein association and dissociation, right? In all drug discovery or wherever signaling or something, all the time protein talk, do their work and go. It is association, dissociation, all the time happens, right? Happening in our body. Two proteins are talking, how they talk? They do not have a vocal cord, right? They talk by meeting. They meet, interact, and then they depart. So, that is kind of association, dissociation continuously going, and if I have to design an experiment of this association and dissociation, one can use the fluorescence anisotropy for interaction or not interacting. I need to have a fluorophore on one of the protein. When they interact, and this you remember, now I am not doing the static experiment, I am talking about dynamics. So, when they bind, complex becomes bigger, the orientation starts changing, anisotropy will be coming into play. So, one can do the anisotropic experiment to understand the protein interaction. Protein like a change in the dynamics of a protein or a conformation of a protein, helix to coil transition in the same protein, right. So, this is all the time happens. Protein all the time changes the structure, it is not that fixed structure that we have. It winds, protein has a very nice motion, एक helix खुलेगा बनेगा, खुलेगा बनेगा, it has a time scale of forming the helix, opening it, forming the helix, opening it. How can I see? If I do crystallography, right, it gives you a static picture. Crystallography is like a taking your photo, one time photo, you are less standing like this, right. And dynamics is happening when you can capture the time resolved motion, right. So, you are like, if suppose I am doing like this sometimes, you can either capture me in this or this state, but you are not capturing what I am doing here, right? I am doing constantly like this, मेरी पलक झपक रही है, you cannot capture if you take one time picture. Sometimes it will be like this, sometimes it will be like this, sometimes it is like this. If you want to understand what is the rate of my palak jhapakna, you need to have a fluorophore here and measure the anisotropy decay, or if I am doing like this, you have to measure that motion that is happening, and these are the techniques where you can really monitor the motion that is captured or happening in these molecules. So, it gives you dynamic picture of helix to coil transition in the fluorophore. How do you measure? Basically, you have a depolarized excitation light, you put a polarization picture, you have a polarization excitation light, your compound which is binding to enzyme, it has a rapid rotation, and you can measure actually parallel versus perpendicular. So, emitted light is again depolarized, but when it is binding to the enzyme, now it is slowly rotating. And now if you are doing the same experiment parallel versus perpendicular, it has not completely depolarized. So, emitted light remains polarized, and you can find it out whether my molecule has bound or not bound. So, that is the kind of assay that we are talking about, enzyme substrate reaction by measuring the fluorescence, anisotropy and polarization. You can put it. Similarly, you can have a fluorescent tracer. So, this fluorescent molecule, organic molecule, freely tumbling in the solution. You measure parallel versus perpendicular, lights are cancelled because of isotropic environment. When it is bound to a protein, now its motion is restricted. So, parallel versus perpendicular will have a difference, and that R I parallel I perpendicular by I parallel plus 2I. So, that will give you value, and you find it has a high polarization value. So, these are some of the application of the fluorescence polarization one can have in biological application that we discuss, drug discovery, wherever you want to have. You can use fluorescence polarization and anisotropy to understand and capture the dynamic picture that is happening. The good part is that it is a low costly. I like low cost involved here. You can get it these pictures by doing more fancier experiment, but हर बार चींटी को मारने के लिए तलवार निकालना तो जरूरी नहीं है ना, right? So, this is the, you can use the simpler system to understand and to do the research. Okay. Next topic is FRET, fluorescence resonance energy transfer. But today before I end, I just want to take a question from you.
And isotropy, how is it making sense? Because proteins are always like very dynamic.
Proteins are very dynamic, that is correct.
Anisotropy also doesn't make sense, isotropy also doesn't.
It makes sense. Nothing is completely anisotropic, nothing is completely isotropic. Suppose this is my fluorophore hanging here, doing like this. Is it isotropic or anisotropic?
Isotropic.
It is isotropic. Same guy is now sitting here. Is it isotropic or anisotropic?
Anisotropic.
It may have local isotropy, but globally it is anisotropic. So, in protein, because here my observation is just centered around fluorophore, right. It could happen that protein is slowly tumbling like this, but time scale is very different. At that time scale, it is anisotropic. The protein is doing all the time very fast, it is isotropic. So, it is a time scale, right. So, in which window we are looking at, protein has a different motion, and in that observational window, because we are measuring nanosecond time scale, right, in using fluorescence. So, in nanosecond this is completely isotropic, but here it is going inside, it is an anisotropic. Okay, thank you.